Hi calculus class. Today we're going to look at more of the ratio test, and I'll also show you what's called the root test, which is basically just a rearrangement of the same thing here in a moment. So let's try to find whether this series diverges or converges. So I think we'll try to apply the ratio test. Let's see what happens. So let's see. We're going to look at the limit as n approaches infinity of -1 to the n plus 1. So you know what, and just thinking ahead, I'm going to be simplifying as we go this time. I think that's probably what you're going to be doing on your problems anyway. So to the n plus 1 is going to have that, and then another -1 to the 1 power, right? So we're going to have that, and we're going to have the square root of n plus 1. That I really can't split apart, right? Square roots don't distribute or anything like that. And then I'm going to have that over n plus 2. Okay, so I'm going to divide that all, just remembering, we're dividing by a sub n. So that's going to be dividing by this guy down here. So that means I'm going to flip it and multiply by the reciprocal. So then we're going to have times n plus 1 on top, square root of n on bottom. And I'm going to put this guy, I'll just pretend it's going to the top. So I'm going to have that guy on the bottom. Okay, let's see what I get my absolute value bar to end for the ratio test. And now I'm going to cancel what I can. So this cancels, and really not a lot else cancels here. So let's see what we've got. So that's going to be the limit as n approaches infinity of, let's see, square root of n plus 1 over the square root of n. Let's see. Well, we still have this part, right? Oh, I guess we could suck these into a single square root. So we could write that as the square root of n plus 1 over n, right? And one square root, product square roots do that. And then we've still got these guys. Dang it, they're still there. So let's think about this. As n approaches infinity, what's that going to be? So we can kind of think about this piecewise. Remember, limits are one of the only operations or operators in calculus or mathematics that allow you to actually think about the limit of this times the limit of that. So we really can think about these two limits separately and go like this, that times that, but I'm just going to do it kind of in my head. So as n approaches infinity, the limit of this guy is clearly 1, right? The order of magnitude on the top and bottom is the same, or you could do it with L'Hopital's rule because it's infinity over infinity. So that's clearly going to be just times 1. So we'll have 1 inside the absolute value. And then this limit, think about what this limit's going to be. Well, as n approaches infinity, inside the square root, we again had the same order of magnitude. So we're going to have 1 inside that square root, so it's kind of like the square root, and then inside is going to limit to 1. I guess I don't even need that. So the square root of 1 is what? Well, I guess that's just 1 as well, so it's 1 times 1, which is just the absolute value of 1, which is 1. Shoot, our ratio test didn't work this time. That's inconclusive if the ratio test works out to exactly 1. So we're going to have to try something else. So let's go back to the drawing board and try something else on this problem. So think about what other test could we use to work on this series. We could think about the absolute value and see if it absolutely converges that way. If we take the absolute value, then we'd have this series, which I think basically if you do some kind of comparison test, I'm not sure that that's going to converge or diverge. So maybe we should try the alternating series test, because of course it has an alternator right there. So let's look at the alternating series test. So if we take the limit of the sequence, not including the alternator term, what does that come out to be? Well, order of magnitude of a root, or 1/2 power, is of course smaller than the 1 power, or a line, so that's going to of course go to 0. Yes, so alternating series is working so far. Now we could look at take a derivative. Let's see. So let's take a derivative. So if we do f of x is this guy, we can try to show it's decreasing. All right, so I'm going to do that. So f prime is going to be ho d high minus high d ho over ho squared. Let's see if we can simplify that just a little bit. Let's see, so we've got a common denominator right there, so I think I'm going to go like this to make that work right here. Nice clever one there. So now we're going to have, it's all over x plus 1 squared. And then on top we've got x plus 1 over 2 root x. And now this is also over 2 root x. So we've got minus root x times 2 is 2x. So that's going to be x minus 2x is minus x plus 1 over 2 root x. Now this is like this. There's the main fraction bar. So if I flip it, it's going to go right there. So that's going to be x plus 1 squared. Okay, so there we go. So all we need to do is show that it's decreasing. Remember, for 1 to infinity, or for 2 to infinity, or something close after that. So is that decreasing from 1 to infinity? We could, of course, do like a little first derivative test chart to see that. Let's just do that, just to remind ourselves of how to do that. So if we go f and f prime, what are the zeros, or in other words, the critical points of this function? So this function has a critical point where the bottom is 0. So if I put 0 into the bottom, that's going to be a place. If I put negative 1 into the bottom, that's going to be a place. And the top, if I put 1 into the top, that's going to be another critical point. So I've got several critical points here. All I really care about is over here to establish that it's decreasing from 1 to infinity, because of course for my series, the only part of the function I'm interested in is 1 to infinity. So I'm going to take that a test point like, I don't know, 2, and I'll toss that into my function. So if I put 2 into my function, then I get negative 2 plus 1, that's negative. And then, of course, the bottom, this term's always going to be positive, and so is that one, if you think about the domain of the square root of x function. So it's going to be positive on the bottom. Negative over positive is negative. The derivative is negative. That means the function is decreasing. Check. We've satisfied the hypotheses of the alternating series test. So that shows that since the alternating series test hypotheses are satisfied, this series converges by alternating series, the test. Okay? So there we go. So sometimes the ratio test, even though it's the big gun, the one that works, it's kind of your go-to test in series, it doesn't always work, and sometimes you have to revert to one of your other tests, like the integral test or alternating series. All right, I thought we'd look at one with an infinite product as well today. Infinite products can be scary just because we really haven't worked with them very much in mathematics to this point. They're not scary if you have the ratio test available, though. So let's see if this one works with the ratio test. I just pulled one out of the book from another section, actually. One of the ones that we had trouble with in an earlier section. Just let's see if the ratio test works on it. I'm not sure, so let's just give it a shot and see what happens. So let's see. The limit as n approaches infinity, a sub n plus 1 over a sub n. There's the test that we're going to be writing out. So here we go. Let's see. So we're going to have a sub n plus 1. It's going to be negative 1 to the n plus 2, which really, if I'm thinking ahead, I'm going to want to cancel an n plus 1. So, I'm going to write it like this. There's my n plus 2. And then this guy, I need to plug in n plus 1 right there. So I'm going to have 1 times 3 times 5 times dot, dot, dot. And then when I plug in n plus 1 right here, it's going to be 2n plus 1 minus 1, which is 2n. 2 minus 1 is 1. So it's going to go up to 2n minus 1, and now it's going to end at 2n plus 1 in that part of the infinite product. So there we go with that. And then we've got, let's see, so we've got 1 times 4 times 7 times dot, dot, dot. And we were ending at 3n minus 2 in the a sub n expression, but now we've got to put n plus 1 right here. So simplify that in your head or wherever, and you're going to go up to 3n minus 2, yes, but then we're going to have an extra term in the infinite product. I shouldn't say extra term, I should say extra multiple. So this is going to be 3n. 3n, 3 times 1 is 3, minus 2. So let's see, let's just be careful there. So 3n plus 3 minus 2, that's going to be plus 1. There we go. And now this time I'm just going to put this all underneath because I'm running out of room here. So then we're going to have a sub n underneath. So I'm just going to copy it all down again. these out of the way. Okay, and now we're going to see what cancels, so we can see if we can actually do this limit and conclude something with the ratio test. So I think a bunch of stuff cancels. This cancels. Let's see. In the infinite product here on top, all of that is going to cancel with all of that. And the infinite product on the bottom, all the way up to here, is going to cancel with all of that. So what's left? Let's see. So this is, oops, I forgot my limit right here. Watch out for that limit. Haven't used my limit yet. So now inside, what do I have left? I have -1 for right there, and I've got that times 2n plus 1. Anything else? I have a 3n plus 1 right here. Anything on the bottom here? Nope, I think we're good to go. So what do we get for that limit? I think that's one we should be able to do, no problem. Let's see, so the order of magnitude is equal on both, so you could use L'Hopital's rule to verify it, or be stronger if you're more comfortable with that. But also, this is a negative times that, so really, if we think about the absolute value, this is the same thing as, if we take the absolute value, it's going to get rid of that -1, and it's going to be this. Yeah? So now, what's the limit of that? It's a super easy limit. Of course, that's equal to 2/3. 2/3 is in fact less than 1, so yes, we do get to conclude that this guy is absolutely convergent by the ratio test. That's a neat problem. Let's look at the root test now. So pretty much the last thing we're going to look at in this lesson is the root test. And the root test works exactly just like the ratio test. It's just basically a reformulation of the ratio test for problems that kind of work easier if you take an nth root instead of taking a ratio of the n plus 1 or next term compared to the current one, the nth term. So the setup is exactly the same. If you have a series a sub n, it's going to converge absolutely. If when you take the limit of its sequence in absolute value, if you take the nth root of that sequence in absolute value, if that turns out to be less than 1, the limit of that sequence, then it's going to converge absolutely. If you take that limit and that limit is more than 1 or infinity, that series is going to diverge. And if you get 1 exactly, that's the only other possibility when taking such a limit, you're going to get inconclusive and you're going to have to go back to one of your other tests like the integral test or the divergence test or something like that. So let's do one example. So here's a problem that is classically set up so that the root test will be real easy to use on it. You could probably also do this one with the ratio test. If you'd like to try that, that'd be a good exercise to pause the video now and try to do it with the ratio test and just see what happens. Okay, so let's see what happens when we do the root test. So I'm just going to take the limit as n approaches infinity of the absolute value. Oh, excuse me. And really, these are all positive terms here, so I don't even really need to worry about the absolute value, but I'm going to do the nth root of e to the 2n over n to the n. So if I take the limit as n approaches infinity, and we should think about this. Do we think this might have a chance at converging in the first place? That's always a good place to start with series, right? Does it have a chance to converge at the beginning? Which one grows faster? In the sequence, the bottom is of course growing much faster than the top, even though that's exponential double growth. So the bottom is growing much faster though, because it's n to the nth power order growth. So we should think that, yeah, this has a chance to converge definitely. Since the sequence is behaving like that, the series might be able to converge. So if you think about your rules from basic algebra, we've got an nth root here, so what power is that going to be? That's going to be the 1 over n power. And now we can just go power to power is of course multiply. So this is going to be the limit as n approaches infinity of e. When we multiply here, 2n over n is of course 2. We multiply here, n over n is of course 1. And now we've got that the limit as n approaches infinity of that thing is going to go to what? It's going to go to 0, right? E squared is just a number, and this guy keeps growing, so we're going to get bigger and bigger and bigger on the bottom, so that of course goes to 0. 0 is, of course, less than 1, so by condition 1 in the root test, we have that that series is absolutely convergent, and of course you need to write that out. So you'd say something like this: therefore, this series is absolutely
Michael Harris, please come to Student Services.
Convergent by the root test. All right, I'll see you next time.